This is a computer simulation from Stanford of large-scale structure, which means that we're looking at enormous clusters of galaxies, not just the formation of galaxies, but formation of huge clusters of galaxies, which we observe to lie on these enormous webs of filamentary structure. And we believe that most galaxies go through multiple collisions over the course of their lifetime. Now, the argument even in astronomy is that those huge structures can't form if we only look at the luminous matter. There hasn't been enough time, essentially, since the Big Bang for such enormous structures to form. And that for them to form, there must be some dark matter that we can't see to catalyze the collapse of material into these huge structures. But still, that's not so bad, but there's lots of this evidence for dark matter. Sorry, I was missing that one. The spooky thing is that, Peter, maybe you want to talk about this aspect, about the amount of dark matter compared to visible matter, that's surprising. How, this assessment of 80%, do you think that that turned out to be a surprising number, or did you think it would go away?
Well, this started coming up about when I was in the field, and one of the arguments was, and this is the way theoretical physicists think, is that there was a number which was the fraction of critical density measured in the universe. So there's a magic critical density that keeps the universe from expanding, and that's one. And if at the time everybody did a census of all the matter in the universe using telescopes and everything, you'd get 0.1, so 1/10. So theorists would assume, well...
You don't mean keeps the universe expanding. You mean it keeps it flat.
Keeps it flat, yes.
That's
Thank
okay.
you.
So the universe is definitely expanding, as Hubble saw.
Right.
But the question was whether or not spatially it was literally flat. Things traveled in straight lines, or if things traveled on curves, if the light from other galaxies traveled on curves.
But the logic was, well, this number is close to 1. 0.1 is close to 1 in certain ways of thinking. Therefore, it's probably 1 and something's missing. And you know, sort of wishful thinking. And I remember in probably 84, 85 hearing this in some seminar, thinking like, wow, that's just like really bad logic. Turned out to be right. Shows you how much I know.
Yeah, I mean, I think the reason why, so this was one of the things which astronomers really didn't care about. They're like, who cares if the universe is flat or slightly curved? It doesn't matter to us. If you look at the origin of the universe, it would evolve away from flatness extremely, extremely quickly.
Yeah.
So in order for the universe to be slightly curved today, 14 billion years into its history, it would have to be perfectly flat except for slightly curved by like 1 part in a trillion, trillion, trillion. And that number made theoretical physicists, 4 trillions? Thank you, trillion, 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 trillion. That made theoretical physicists suspect that the only stable value is if the universe is exactly flat, right? So that started to be an argument that maybe there's something missing if the only luminous stuff in the universe makes up for much less than that. I wanted to show this about this. I just found this graphic. I think it's a NASA graphic, but I'm sorry, it might be the European Southern Observatory, where they're showing how we can discover that there's matter out there that we can't see. I mean, how could we possibly know that there's matter out there that we can't see? One way is by looking at the effects of matter on light. I'm going to start that over again. I don't know, Peter, you want to do this one? You've never seen it before. Elena, you want to try it?
Yeah, that's fine.
Go for it.
To me, this phenomenon of gravitational lensing, as we say, is the only way visually that we can bring to you or to us when we say there must be dark matter there. So that's this gravitational lensing, which of course...
I'll just keep replaying it while you talk about it.
So Einstein predicted long ago, I mean, it was expected that the presence of a mass bends light, And so that's essentially this phenomenon. If you're looking from Earth at this galaxy out there, and in the middle there is this big blob that she's showing, which is probably a cluster of galaxy. So there is a big mass full of dark matter, as we know now. So the image of that object that we are observing, in that case the galaxy there, will be distorted because the light from that object will be bent by the presence of that mass. So mass bends light, which is what is predicted, but usually, so if you think of light rays coming from that object, you would expect to come straight to your eyes if you are on Earth or your telescope, but those rays of lights are bent by the presence of mass, and so you will see a distorted or multiple image of that thing. And since you're not really aligned, your eyes or telescope are not really aligned with that object, you actually get a whole, let's say, cone of images, and the projection of that cone is going to be a circle, the so-called Einstein circle. And because we're not aligned, actually the circle is split in little pieces. So if you have these little distortion that you see here are the are the images, split images of that galaxy that we are observing because of the presence of mass, of gravitational mass, the dark matter, in between us and the object.
Yeah, so we see these
you see these
broken
arcs of circle.
And that's really the distant galaxy that we're looking at, smeared out on the sky, which is telling us there must be some big mass between us and that distant galaxy. So even if you can't see that big mass, you deduce it's there by seeing this funny lens, just as if you looked at an object in this room through a completely transparent lens, you would understand it was there by how it distorted the images behind it. And that's exactly the phenomenon.
It's a crappy lens, though.
It's a crummy lens?
Yeah, I mean,
how do you mean?
It smears things. It doesn't focus, we're used to good lenses.
It's not a good pair of
But
glasses.
that's why we do all these beautiful